Hi everyone, my name is Shaban Mchomv and today we are going to proceed with our solving session. Today we are going to look on the topic of differential equations, and this normally is question number 7, particularly in the Advanced Mathematics paper 2. And this is the year 2025, and that's what the question brought for the part of differential equation. The question has got 4 parts, and let's see case A. In case A, we are told to find the general solution of the following differential equations. So here we have Roman 1 and Roman 2. Case A, Roman 1, solution for dy over dx minus y over x equals to x squared. So we are told to apply the techniques in differential equation, where normally we used to apply integration and the differentiation techniques so as to simplify this differential equation until we get now the equation, the responsible equation that were there before. So here, the nature of this is a linear first order differential equation where we can apply the concept of integrating factors, because the nature how it looks like here, condition for exactness does not work. So this relies on the concept of integrating factors. So having said that, now we can say solution. This can be written as dy to the dx minus 1 over x times y equals to x squared. So now I can letting the function of xp equals to this negative 1 over x, these coefficients of y here back. Now from integrating factors, integrating factor, which is given by e integral of p of x with respect to x. So this now becomes e integral. P of x is negative 1 over x now dx. Now this becomes, when we integrate this, because this now gets out, negative 1, now we remain with this one. So dx, so here integrating factor now becomes e, then you can say negative ln of x, whereby this is e ln of x negative 1, which is the same as say x negative 1, which is 1 over x. Yes. So integrating factor, so we have 1 over x. Now after getting the integrating factor, we are going to multiply by this integrating factor both sides of the differential equation. So this become 1 over x times dy dx minus y over x equals to x squared times 1 over x. So here it is going to be 1 over x dy dx minus y over x squared equals to x. So from there, the expanded form of this one, now we can condense it to have simple form that becomes the same as say, formerly we were integrating y over x with respect to x now equals to x. So it was just like that. And up to that point, now, because here it means you kept constant 1 over x, you differentiated y, that's why you had remained with dy dx. Then you plus, you kept constant y, then you differentiate that x, that's why we end up getting xc 1 over xc squared. So from here now, we can apply variable, we can multiply by dx both sides. So we have d, then y over x, this equals to x dx. So from there, now we apply integration. So d, then y over x equals to x dx. If you apply integration both sides, you end up getting y over x equals to what? This is x squared over 2 now plus c, the constant. So from there, if multiplied by x at every term, we end up getting y equals to x cubic over 2 now plus cx. And up to that point, we have obtained now the equation, because we are told to find the general solution now. So this becomes the general solution for that differential equation that employs the use of integrating factor, where the differential equation is not exact. So integrating factor can work. Roman 2, we are provided with the dy dx now minus x tan of y minus x equals to 1. So from there, how do we start? We can start by letting maybe y minus x equals to another variable, maybe v or u. So we can say solution. So letting maybe u equals to y minus x. So after letting now, we can differentiate now du with respect to x. Du with respect to x. So here you'll have du dx is less small 2. The derivative here will be, so we remain dy dx because it will be 1. And here it means we differentiate implicitly. So minus 1. Here we differentiate normally. So we don't leave the differential coefficient. So from there, now we can make subject to dy dx, so as we can substitute here. So now we can say dy dx now equals to what? It is 1 we plus du dx, because we can just take this one to the other side. Up to that point now, we go back to the original differential equation. Where dy dx now we put 1, we plus du dx minus x tan of u, then equals to 1. So this 1 and 1 now cancel out. They cancel out. So we have du dx minus x tan of u equals to 0. So from there, we can apply variable separation. Variable separation. So it can be easier for integration to work. Now du dx is the same as say x tan of u. Now from here, we'll have du over tan of u equals to x dx. So we have something like that. And this tan du over tan of u, 1 over tan, we know it's cot of u du. Now it is x dx. So from here we can apply integration to see what we have. Integrating cot is the same as say cos of u over the sine of u du equals to, here will be x squared over 2 now plus c. So from there, if we let maybe p to be sine of u, it means we'll end up getting now ln of sine of u. For example, here, if you let p, it is sine of u, it means dp du, it is the cosine of u. Now, dp the same as say cos u times du, which is this much. Co-integral of dp now over u, that's ln of u. So here, you'll have ln of p. ln of p, which is p now we say it's sine of u. So introduce this absolute, then x squared over 2 now plus c. So from here, This can be expressed in exponential form or in logarithmic form, as it's a log of the sine of u, then to base e equals to x squared over 2 now plus c. So from here, if we express in exponential form, we are going to end up getting sine of u equals to e, then x squared over 2 now plus c. So this is the same as say e x squared over 2 now times e raised to c. Now we can let that e raised to c equals to a constant a. So sine of u now becomes a e of x squared now over 2. Now from there, we need to replace that letter u by that. Remember, we have let formally, we said y minus x equals to u. Y minus x equals to u. That we said formally, u equals to y minus x. So here it will become sine of y minus x equals to a e raised to x squared over 2, where a is a constant. A we know is a constant. So up to this point here, we have found the general solution for the differential equation, this Roman 2. So it is a sine bracket y minus x bracket equals to a e raised to x squared over 2, where a is a constant, which is equals to e raised to c. If that to be the case, let's see part B. Now in case B, we are told to eliminate. It means now eliminate the constants a and b in the equation. We don't want to see a and b. We want to see other things, but a and b should not be there. So it's a matter of elimination now. Given x equals to a, the cosine of 2t, now we plus b. Now solution. So the first thing that we are going to do here in this problem, we are going to perform differentiation for the first time, for the second time. Until now, a and b are cancelled out. So for example, if we differentiate x with respect to t, because a and b are constants, it means the variable is t and x. So here becomes dx to the dt equals to derivative here. It means the derivative of inside here, the angle, will be 2 because we are differentiate here. 2t becomes 2. Now it is 2 times the derivative of cosine. We know it is negative sign. Then a now sine. Then we write sine of that 2t plus b. So if we do by direct substitution, you end up getting that. Yeah, for example, like maybe taking u equals to 2t plus b. If you differentiate and later coming to apply chain rule, you'll end up getting negative 2a sine of 2t plus b. But now there is a possibility, if we try to differentiate this one again, once more time, we are going to form something like this, where now we can replace it by x. And from there, a and b now will be ignored or eliminated. So if we perform once more differentiation, the second derivative with respect to t, the derivative of here is 2. Again, it will be negative 4a. Then of sine now will be positive cosine. Then 2t now plus b. Now, but that a cos of 2t plus b bracket equals to x. So we find, we make some environment where we can have a cosine bracket of 2t plus b bracket. So as we replace by x here. So it's the same as saying, here it is 2, negative 2, then now we have 2a cosine of 2t now with plus b bracket. So we'll end up getting -2, but sorry, this -4 has to go out because we need a cosine. Then a cosine of 2t plus b. So it has to be like that. I thought here maybe it was 2 here. But if not 2 here, now the whole 4, -4, we take it out. So it has to remain like that. So if that to be the case, then now it will be the square of x dt squared equals to what? Equals to -4 now, where a cosine of that angle now become x. So here it will be -4x. And this now mark the solution now. So that will be the solution, but it means it's a differential equation where now we don't see a and b. It means we have eliminated a and b. And some problem that of trigonometry appears to be the solution set if it appear to be like this. If you want to eliminate these constants, we perform several differentiation. If you perform derivative of the first, the second, then we see they'll come because differentiation of cosine is sine, of sine is cosine. So they get to repeat in some multiple numbers of differentiation, where now you can substitute the previous expression. And by so doing, you'll be cancelled out or eliminating those constants as required. Now, part C, in part C now, this is just an application of differentiation. Now let's see, a particle P falls vertically under gravity, so it's a kinematic problem. The air resistance of the falling particle is taken to be proportional to its speed. You see, speed at any instant. So it means now relative velocity is somehow proportional to the air resistance. So the distance x at which the particle has fallen after t seconds is given by the differential equation. This is what now we are in need of, the displacement equation. So this one, so we are given the square of x with respect to time equals to g minus that's k then dx dt. Yes, where k and g are positive constant, then you require to find the distance x as a function of t given. So the distance x as a function of t. It means we need to end up getting xt, this much. Given the initial condition that dx dt, it is 0 and the x equals to 0 when time equals to 0. Now from this problem, here we need to start solving by finding the general solution. So from this differential equation, so we can add that k then the x dt equals to g. It means we have shifted to the other side. Now I can term two things. For it to get general solution, I need to deal with these homogeneous and again to deal with a particular solution. So on taking the homogeneous, part, that the xc this squared plus k then the x dt, now we assume equals to 0. So from here, now we can let then now we say then setting maybe v equals to the x dt. It means the v dt equals to the square of x dt squared. So equals to that way. So if that to be the case, now we substitute back here to the homogeneous. So here you will have dv dt. Now we plus k. Dx dt is v, now equals to 0. So on apply variable separation, you have dv dt equals to negative kv. So dv over v equals to negative k now dt. If you apply integration now, you'll have ln of v equals to negative kt, now we plus c. So here, if we go for exponential, it means will be logarithm of v to base e, which is less more to negative kt, now we plus c. So v equals to e raised to negative kt times e raised to c. And now v equals to a, then e negative kt, whereby this e of c equals to a constant. This becomes a constant. So from there, you'll have v equals to a e of negative kt. Now, up to that point now, we have known what is v equals to a e raised to negative kt. And now we can replace this v by the dx dt. So if we replace by the dx, now dt will be equals to a e negative kt, this way. So from there, this now we can say that is the homogeneous solution part. So we need to go for the particular solution part, there g. If this g is constant, as we are told here is constant, now we can let something to represent the particular solution. So if that to be the case, so now we say, let this maybe the function of x of t, the x function of t now equals to a certain constant b of t, this one. Sorry, just become, yes, yeah, bt. So if we differentiate now dx with respect to t, here becomes b. And now if we perform the second derivative, now it becomes 0. So we go back here and we substitute the values for dx dt and the square of x dt squared. So from here, from the homogeneous part now, if we plus that k, then dx dt equals to g. So this is 0. Now we plus, here will be b, so it is kb equals to g. So now the value of b here becomes g over k. G over k. So now, if we are looking for the general solution now, the general solution is a matter of saying now dx dt equals to the homogeneous part that we obtain a raised to e negative kt. Now we plus this particular, that will be g over k. So we go now for the initial condition that we are provided with. We have dx dt equals to 0 and the x equals to 0 if it's happened, but here we don't have variable x when time was 0. So we can assume that this dx dt equals to 0 when t equals to 0 also. So we substitute so as we calculate the value of constant a. So we need to know what is a. Then now here becomes 0 equals to a. If this t is 0, it means e of 0 is 1. Now we plus g over k. So the value of a now here becomes negative g over k. So we go back here, we substitute dx dt now equals to negative g over k e, then negative kt here. Now we plus g over k. After that, now this is dominated by t, so we can apply variable separation. So as we integrate and see how we eliminate other constants when t and x are 0. So by variable separation, now we say by variable separation, we have, so it becomes dx equals to neg g over k e raised to negative kt. Now we plus g over k bracket, then dt. So dx here, if we factor out g over k, or negative g over k, here inside becomes e negative kt minus 1. Then now dt, we go for integration. So we get x equals to this neg g over k out. Now we integrate e neg kt minus 1 here. So dt. So when integrating this part here now we end up getting integral of this, and then we take integration inside. So if we take integration inside here, we can use the technique that 1 over derivative of this times the original function e. So derivative of this, we know here it is negative k, so will be negative 1 over k times e raised to negative kt. So that will be the integration of that. Minus integral of dt, we know it is t, now we plus another constant, maybe d. So from here, you'll have x function of t equals to, when you try to multiply now, you get g over k square, then e negative kt. Now we plus g over k times t, then we plus the constant d. So from here, if we apply initial condition that when x was 0 and the time was 0, because we don't have dx dt there, so we can say x is 0 when the initial condition, then time was 0. So we'll have 0, where x, now we put 0, equals to g over k square. Now here will be, when this is 1, it will be 1. Then here now will be 0. Then we plus d. It means the value of the constant d will be neg g over k square. So it will be negative g over k square. So now the function becomes, therefore the function becomes, so it is g over k square times e raised to negative kt. Now we plus that g over k times t, then now we plus d minus g over k square. So from there, if we factor out this one here, g over k square, we can have simple equation, but up to that point, we have simplified, we have done the parts of the function to express the distance x as the function of t with this initial condition. So if we simplify more, you will end up getting so it becomes the function x of t, factor out this, so it will be e negative kt. Now If we add here, it means g over k. When we divide by that times k squared over g, cancel out. So it remains k plus k, kt. Then we minus 1. So that's how it becomes. So that will be the function of x with respect to, will be the function of the distance x is the function of t. Now we are through with the part C, so let's move for the part D. We are told to determine the solution of the differential equation, that one, given the initial condition x is 0, y is 2, and the derivative dy dx equals to 3. So case D, so that is 2x minus 1. Now the square root of y dx square minus 2, then dy dx equals to 0. Given the initial conditions, that x equals to 0, y equals to 2, and dy dx equals to 0, equals to 3, sorry, equals to positive 3. Now we can solve by letting, so here we can just letting dy dx equals to maybe equals to p. So if we differentiate now, dp with respect to x will be equals to the square root of y dx squared. So up to that point, we are going to replace this second derivative by dp dx, and that dy dx by p. So you'll have 2x minus 1 dp dx minus 2, then p equals to 0. So from here, we have simple differential equation, first order, where we can apply variable separation technique so as to integrate and getting the solution. So it will be 2x minus 1, then dp dx equals to 2p. It means you have taken that 2p to the other side. So from here is for variable separation. So with the same as say dp over p now equals to 2 dx over 2x minus 1. So that is variable separation. Variable separation. It means p to the side, left hand side, and that x is to the right hand side. We have separated the variables. So if that to be the case, now I can apply integration. So now we can say integral of now dp over p equals to integration of 2 now dx over that 2x minus 1. So when integrating 1 over p dp, here we end up getting ln, natural logarithm of that p, equals to what? Here, we can just let, by direct substitution, if we let maybe u equals to 2x minus 1, it means du dx equals to 2. So if you make subject to 2 dx, it means du now it is 2 dx. Now if you go back there, 2 dx now we put du. Over this one it is u. So we end up getting ln of that 2x minus 1. So here it becomes ln of p equals to ln absolute bracket 2x minus 1 absolute. So we end up getting something like that. So if that to be the case, you need to be, you have mastered already differentiation and integration well. So here we plus constant c, arbitrary constant, because here is not the matter of limit, so it is indefinite integral. So that arbitrary constant has to be there, the decisional constant c. So now ln, so I can group them, minus ln absolute 2x minus 1 absolute equals to c. So this become ln now of p over that 2x minus 1. So this equals to c, because when you subtract, you divide. They have the same base e. Now, on undergoing transformation from logarithmic to exponential, this goes to be log of p over 2 minus x base e equals to c. So p, expressing now to exponential form, will be e raised to c. So from there, p becomes, that will be now 2x minus 1 times e of c. But we can let maybe a equals to e of c, because that is constant. That is the constant, still constant. So from there, we remember we let p, it is dy dx. So we can say p, it is dy dx equals to 2x minus 1. Now you times that a. So from there, we can apply now the initial condition, so is when we can solve for the value of a. So we can say the value of x equals to 0, whereby dx dy was 3. The reason here is to get the value of a, where we say a is a constant. So now this becomes 3 equals to 2 times 0 minus 1 times the value of a. So from there, it will be 3 equals to what? Negative a. So a equals to negative 3. Then, now dy dx is less more to say, because a now is negative 3, it means when we take it inside, this becomes negative 6x plus 3. Because negative 3 times 2x, it is negative 6x, and negative 3 times negative 1, you get positive 3. So from there, dy dx equals to negative 6x plus 3. But now that's not the solution. So we need to perform another variable separation so as we can integrate in getting y equals to what. So again, we can say by variable separation equals to negative 6x now plus 3, now you times dx. So on applying now integration to both sides, so we'll have something like this. So here, when integrating dy now, here we have y equals to what? Here, if we take integration inside, you will have negative 6, then x now will be x squared over 2. Now we plus 3x, we plus another constant, maybe d. Another constant d. So you'll have y equals to negative 3, because negative 6 divided by 2 is negative 3x squared. We plus 3x, now we plus d, where d is a constant. So if that to be the case, we go back to the initial condition that we are provided with. We know y, we know x. X is 0, y is 2. So this can help us to get the value of that constant d. So we go back again. So now we say since x equals to 0 and y equals to 2, then, so here we put 2 where y, equals to, where x now we put 0, so here will be 0, 0, now we plus d. So it will be 0 now plus d. So now d becomes 2. Now, the solution now becomes y equals to negative 3x squared. Now we plus 3x, then d is 2, we plus 2. Up to that point, we have managed to get the solution for the differential equation of this part B provided with the initial condition. And up to that point, we are through with question number 7 in the year 2025.